scientific method here, and we have a very elementary way of thinking about the scientific method there. It's even drawn out like an elementary class would be. So number one, memorize. It's an observation, then a question, then research, then a guess. It's not that simple. You might have been taught that and told you have to memorize this setup exactly. It's not that simple. You saw it with that chart yesterday. It's just not that simple. So we're going to talk, oops, we did that part already. We're going to talk a little more in depth about it. So when we have a problem or a question, this part's written down for you already, something you want to know more about. You could just want to know more about something for the sake of knowing more about it. Real world example, maybe I want to know more about rheumatoid arthritis. How did I get rheumatoid arthritis? What makes somebody get it? So I do it just for the sake of knowing it, and that's called pure science. So when you're researching something just for the sake of knowing more about it, we call it pure science. If I want to solve a problem or improve a way of life, for instance, now that I know more about what rheumatoid arthritis is, maybe I want to find a cure for it. I want to improve not only a way of life, but my way of life. So I go out to the medical field and I try to find a cure for it. That is called one of two things, either technology or two, applied science. So it's not just for the sake of knowing something, it's because we actually want to solve a problem or improve a way of life. What I tend to do when we take notes is look for people writing, looking up, looking down, looking up, looking down, and when most of the pens have stopped, I'll move on. Some of you are super fast writers. Thank you for being patient while other people finish up. I can also generally tell if somebody's just doodling, so I won't be waiting on you if it looks like you're just doodling. I feel like there was one more thing I wanted to say. If I say something is important, or if I repeat something multiple times, or if I say this will be on a test, I recommend you write it down. Whether or not there's a space for it on here or not, I recommend you write it down. Questions on problem and question before we move on? Okay. Next then is a hypothesis. It's a prediction of what will happen. Or it explains why something happens. That's exactly what I was just thinking of, Eric. So I could make a prediction that if I drop my pen, it's going to fall and hit my desk.
Oh, I just did that accidentally.
Yeah, well, that was perfect because I was just thinking that I was going to drop something. It's same wavelength. That's excellent. Thank you for demonstrating that for me.
So I'm a TA. Teacher's assistant.
Sure. You all are teachers' assistants at some point, but you were right then. That was perfect. Or it explains why something happened. So if I say, when I drop my pencil and it falls to the ground, it will stop because there is another object there made out of particles that are too close together for it to go through. That would be the why.
So go on the left one.
Yeah. By this time of day, I'm very tired and do tend to ramble, so let me know if I go too fast. Okay. When you have a whole bunch of hypotheses that are supported by a whole bunch of data, you can use them as the basis for a theory. We're going to talk a lot about theory later on in the notes today. Okay, an experiment. You've got this part written down already. It's an organized procedure for testing hypothesis. I want to go a little more in depth into these three things. So it includes a purpose. Why are you doing it? If you're just doing something for no good reason and you're not trying to solve something, you probably shouldn't be doing it. And if you're doing that on an IB lab, they're going to like, why are you doing this? They need that explanation. So know that you need to talk about purpose when you're doing an IB lab. You have to, in the IB labs, specifically document every part of materials that you are using, and in a very specific way. So if I, rather than sulfuric acid, had used a very concentrated acetic acid on the egg on Tuesday, that would have done the same thing the sulfuric would have. And acetic acid is vinegar. Except in a very concentrated form, we don't call it vinegar anymore. The vinegar that we use is very dilute. It has a lot of water in it. It's not as concentrated as it had been before. So if I splashed vinegar in my eye while I'm cooking some sauerkraut, then it's gonna burn maybe a little bit, but it's not gonna rearrange the proteins in my eye and cause permanent damage. I'm just gonna wash it out and I'll be fine. Well, if I got concentrated acetic acid, which is the vinegar but concentrated, that's gonna really hurt my eye. I want to tell the difference between those in my materials. If I just say acetic acid, IB is going to ding your grade. You're going to say, well, you're not telling me what amount. How concentrated is it? So being very specific about materials. I might underline that one if I were you. Be specific about materials. And then another issue that we've run into in the past is with the procedure. Some people are really good in their English classes at writing very beautiful, flowery essays, 5-paragraph essays that are very technical and beautiful and wonderful. That's not what we want here. We want step-by-step directions. Step 1, do this. Step 2, do this. Step 3, do this. If you start getting into this really beautiful, that sounds all good, but it's not going to be easy to follow. I want things that'll be easy to follow. So maybe under or by procedure, do a little line and say step by step. We have 3 main types of variables that you would have to talk about in your experiment section of a lab report. One of them is the independent variable. That is the thing that the experimenter changes. I like to think of this as the thing that I change. I'm the experimenter, this is what I change. Which helps me a lot because independent starts with I. It is the thing that I change in the lab. And there can only be one thing that I change. If multiple things start changing, then I don't know what is having the effect on the thing that's being changed. Yeah, Mohammed.
Maybe like one group. Like a group of things. Like you just have 2 groups, like a control group.
You could have a control group that doesn't have anything changed, and that could be part of your design. That's true. Very true, Mohammed. Thank you. The example that I've been using today is, again, with the rheumatoid arthritis. The first medicine that they had me on was called methotrexate. It's also a cancer drug. They give it to you in much smaller doses than they give to cancer patients, though. So they give me a small dosage. I kind of feel maybe a little bit better than I did before. And so they're like, well, maybe we should increase the dosage. That's the doctor, the experimenter, saying, I am going to change this for you. They're going to increase the dosage. Well, if he also said, not only am I going to do that, but I'm going to give you another medicine to use with it as well, and then I started feeling better, I don't know which one of those two had the positive effect, or if it was the effect of both of them together. So a good experiment that my doctor could do is say, okay, we're going to increase the dosage of this and see what it does. And then if that doesn't do anything, he's going to maybe go back to the original dosage and say, okay, we're going to try this med along with your original dosage. But never at the same time. if we want to pinpoint what's making the change. So one thing only. Also, one thing only, the dependent variable. It is the thing that changes as a result of the independent variable. At least it's what we're looking at in the experiment. Now, when they increased the dosage of my methotrexate, it didn't really make me feel any better, and it made my stomach really upset. So we could kind of say that the dependent variable, this is changing because of the medicine, but it's not what I was studying in the experiment. I was studying the does it make me feel better. I was not studying does it make my stomach upset. We get that information, but that's not what I was looking for. So really I have one independent variable and one dependent variable. 1 and 1. Your homework assignment, you're going to have 1 and 1 for each of the problems that you're given. 1 independent, 1 dependent. One thing that you're looking for. Other things might change along the way because of your one independent variable, but you're really only researching one of those things. Now, this last one, there's going to be a lot of. The control variables. Those are those things that we could have as independent variables if we wanted to, but it's not what we're looking for. They're things that we're going to hold constant. It's anything that could affect the dependent variable. So we need to keep it the same throughout the experiment. And again, we've got 1, 1, and a whole bunch. 1 independent, 1 dependent, whole bunch of controls. And if we're doing a lab for IB and we send in one that doesn't have 1, 1, and a whole bunch, they're going to say, this does not get full points. You're not being clear enough here. You're not going to find any results because your lab is not designed well. And we want to avoid that. We want all those lab points. Okay, I still see some pens going, so we'll wait here a little bit longer. I hope to have clickers up and running by tomorrow, but I don't have them today. So we're going old school. You're going to use your fingers to represent different letters. Either 1 is going to be an A, 2 is going to be a B, 3 is going to be a C, 4 is going to be a D. And here's our thing. So Tommy likes to eat mac and cheese after school every day, but doesn't like easy mac or waiting for the water to boil. First world problems, right? He heard in science class that adding table salt, which is sodium chloride or NaCl, will slightly increase the temperature at which water boils, and a higher boiling point would make, theoretically, the noodles cook faster. He's not sure how much salt would be needed to be added in order to see a decrease in the amount of time to make his mac and cheese. So that's the overall statement. Excuse me. A is going to be independent variable, or 1 is independent variable. 2 is dependent variable. 3 is the problem, and 4 is the hypothesis. And I just want you to hold up your hand with what you think it is so I know that if you're on the right page or not, or on the same page as everyone else. So, taking this bit by bit, he likes to eat mac and cheese after school, but doesn't like easy mac or waiting for the water to boil. Would that be independent, dependent, problem, or hypothesis? I'm seeing a lot of 3s. That is a problem. That's his problem. He heard in science class, blah, 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 higher boiling point make noodles cook faster. Would that be independent, dependent, problem, or hypothesis? Nice. We've got a lot of hypotheses held up right now. Good. Yeah, that's his hypothesis. So the next part, the amount of salt that he adds, would that be IV, DV, problem, hypothesis? The amount of salt that he adds. Yeah, it's the thing that he is changing. I change it, independent variable. A, good. And then the amount of time for the mac and cheese to cook, what would that be? Good, I see a lot of DVs, dependent variable, absolutely. By his hypothesis, that should change as a result of the amount of salt that he added. Good. Questions so far? Okay. One more thing for the front side of the page, then we're moving on to the back. So observation of data, it's just seeing and recording what actually happens. This next part, don't write. I have it in italics so that you won't write it. Who remembers the two types of observations we can make? And I've heard lots of different possibilities today, but there's two things that I have in my mind. I think you're thinking changes, and we could have physical or chemical changes. That's good. That's getting us ahead of the unit. But that is good. Yeah. We could have experimental and anecdotal. That's not what I'm looking for here. Oh, I thought you were raising your hand for a second. I got excited. Both of the words start with Q. Yeah, the quantities and qualities, quantitative and qualitative. So qualitative is just using the 5 senses. He's tall. That would be a qualitative observation. I could make a quantitative observation if I actually use a measuring device. He is 6 foot 7 inches. Rather than he's tall. And then you can flip over the page when you're done writing that. Slide 5 is completely written for you already, but I put this one in all caps. You think it's important? Yeah, you might want to put a star or something by it too. So analysis is organizing the data using graphs, tables, etc. But the real key here is actually thinking about what this is telling you. And this goes directly in line with what the next slide is talking about, which is conclusions. So now that I'm actually thinking about what the data is telling me, I'm going to start looking to see if the data supports the hypotheses. So, IB has 3 sections of what it considers a good lab to have. And there's big rubrics that are really quite vague, explaining very vaguely what each of these mean. We'll try to get as specific as we can later on. For now, I just want you to know what the acronyms are. So when you see D, that means we have a design lab. You're going to come up with the hypothesis and the problem and the independent variable and the dependent variable and all of the controls, and you'll write out what your experiment would be. Now sometimes we will actually carry out those experiments, sometimes we won't. Sometimes you will design a lab just for the sake of designing a lab. Sometimes you go from the design and you collect data for it. Data collection and processing. So maybe you design a lab to figure out the density of an unknown. Wouldn't be the best design lab, but we could design it. And then you collect all of the values, and then the processing would be doing the calculations. Sometimes I'll give you the design, and all you have to do is the DCP. A lot of the time, your DCP and your CE will both be graded together, which is pretty nice because if you've already done all the data collection and processing, it's not that much more to take one more step and do the conclusion and evaluation for it. Sometimes you'll only do a conclusion and evaluation. Sometimes we won't do official IB labs, and you'll just do a regular old lab that you would have in any class. Okay, we talked about this a little bit yesterday, but we'll look at it again. We know that it's not that linear. It's not as linear as that elementary picture that we had on the very first slide. It's much more like this, which is the handout you got yesterday. Extra copies over there if you need them. The exploration and discovery really is what that problem, question, hypothesis is. That all fits under that portion. The experimenting is that big green, well, it's green here. It's not green on yours since yours is in black and white. The big green circle. And then the bottom two are really what's influencing what we're doing. And so this is me getting up on my soapbox, reminding you all to know your sources. If you're watching the news, know where the study's coming from. Figure out if it was a good designed research study. Figure out where the money is coming from that is paying for that research study. Don't just take everything at face value. I'll get down from my soapbox now and we can continue unless there's any questions on this chart right off the bat. There was a big bird that just flew by the window, sorry. Okay, here's another way for you to get involved. We'll do 1, 2, and 3 this time. Mo wants to know how music style affects plant growth. His hypothesis is that he thinks an upbeat, fast-paced song will make plants grow faster. I'm going to show you a whole bunch of different variables, and you're going to tell me if it's the independent for this experiment, the dependent for this experiment, or if it's one of the controls. Remember, 1, 1, and many. So we should see a lot more C's than we do of A's or B's. Okay, the type of seed. What would that be? Hold up, 1, 2, or 3. In this experiment, I see a lot of 3's. Fabulous. The amount of water. Excellent, I would want to control for that as well. Good. The time that it is watered, and this could either mean the time of day that you do the watering, or it could mean the length of time that you put the water on it. Either way. Yeah, either way it's a control. Good. The height. No, sorry. Good clarification. No, the height of the plant. Yeah, that's what I'm measuring. That's my dependent variable. That's what hopefully will have an effect based on my independent variable. The fertilizer type and amount. Yeah, I'd want to control for that. Good. The music style. Excellent. The independent variable. And the music volume. Awesome. This one threw off the last couple of classes. It is a control. Good. Good, good, good. Questions on that? So let's go into, we're going to talk about theory, hypothesis again, and laws, because these are things that get a little bit philosophical, a little bit based on semantics, and I want to make sure it's really clear for us. So a theory is an explanation of why something happens. Why something happens. The independent variable, we remember because there's an I with the first one, it's the thing that I change. We can remember theory here because it ends with a Y. It's an explanation of why something happens. It's based on many experiments that support the hypothesis, whatever that hypothesis may be. It's a big idea to answer a big question. Here's the kicker. This is the thing that throws people off. A theory can never actually be proven. And again, we're getting kind of into semantics here. What does it mean to prove something? What does it mean to have a theory of something? Do you have something to add to that?
I was going to say why.
What was that? Oh, do you know?
Well, Miss T said if it was to be proved, it would be a log. Not a log. Said every single time that you would do it, it has to be the exact same thing. So for every single experiment.
Okay, I think I know exactly what she was trying to get across. I don't think it quite fits in. Sorry. I think I know what she was going for there, but we'll see what that law is in a minute, because I know that's what she would have said for that. The theory is just the best explanation that we have so far with the data that we've collected. So you probably know from history that at one point, the Earth was at the center of the universe, or so they thought.
And it was flat.
Yeah, and we kind of laugh at that now. Kind of giggle when we hear that, like, oh, I can't believe that they thought that. But they had data, they had observations that supported that theory. They had a lot of stuff that told them, yeah, this is the way it is. But then new data came around. And you know, sometimes when this new data comes around, people are like, yeah, I'm not buying it. No, and it takes a lot of forcing, a lot more data, a lot more scientists getting on board before some of these really big ideas can shift in any way. It wasn't an easy thing to say, no, actually the sun is what we go around. The sun doesn't go around us. Okay. Hypothesis. I said we'd come back to it. It's a basis for a theory. These also are never proven. It's merely supported or not supported by whatever data we get. If the data doesn't support it, it can be improved and retested. Or the experiment could be improved and retested. Sometimes our experiments are bad. If the data does support it, we could start getting enough data and enough scientists to basically end up with a new theory. So a hypothesis can go to a theory. This next one is where a lot of people end up getting confused, even sometimes teachers. The law. Scientific law. It's a summary of many observations. If Eric drops his pen again, it's going to fall until it hits something. I can see that observation happening over and over and over again. Exactly. Thank you. You are being a very good TA today. It tells what will happen if something else happens. So if he drops it, it will fall until it hits something. Here's where people get confused. It's not saying why something is happening. That belongs to theory. Theory has a Y at the end. Law does not have Y in it anywhere. Okay, it does not explain why that pen is going to fall until it hits something. It's also never proven. So we have three things here that are never actually proven. It's supported by the available data that we have, just like the other two. And if new data comes around that contradicts it, we have to revise and revisit our law again. So that's similar between all three of those. They're never officially proven, and they might be changed. We're going to do another you showing me fingers. 1 or 2. Please be appropriate with your 1. I should have said that earlier. Make it your pointer finger or your thumb or something. We've got either 1 theory or 2 law. I'm going to just give you 2 statements. One first, then the other one. Think about what is it really saying. Is it trying to explain why something's happening or just saying that it is happening? So, the Earth rotates around the Sun in a periodic manner. Is that A, a theory, or B, a law? Good. Lots of laws there. An object is dropped from your hand and will fall to the Earth due to gravity. Yeah, that's explaining a why, so it is a theory. It's saying how is it happening. It's just not saying that it's happening. So it's a theory. Questions on that at all? Your homework's going to